We defined momentum the very first day of class as how difficult it is to stop an object. And of course, that translated into the product of mass times velocity, right? It's difficult to stop an object when it has a lot of mass. It's difficult to stop an object when it has a lot of velocity. Yesterday, we extended that discussion of momentum into a conservation law, another conservation law, the law of conservation of momentum, which in its most basic form says that momentum can't be created and it can't be destroyed. We use that, however, in an isolated system. And when we look at an isolated system, we find that there's never going to be any momentum gained or even lost. In other words, the total momentum will remain the same. If one object gains momentum, another object will lose momentum, so that the total amount of momentum will remain the same. I mentioned that word isolated. What do I mean by isolated? An isolated system versus a closed system or versus an open system. Yeah, nothing can get in or out. Now, strictly speaking, that means that no matter can get in or out, and no energy can get in or out. Both of those are important. You can't have any matter go in or out of the system, otherwise it messes everything else up. You still don't create or destroy momentum, but you will gain or lose momentum. Okay? You can't create it or destroy it, but you will gain it or lose it from some other source. We can't have any mass going in or out, but that's pretty obvious, right? The less obvious one is the energy. We also can't have any energy in or out. In other words, we can't have any what acting? Any forces, any external forces acting on the system. If we do, then we're either going to add energy or we're going to lose energy. Friction will take away energy and therefore momentum. Wind might take away energy or it might add energy and therefore momentum to the system. Okay, we don't want to have any external forces. That gives us an isolated system. Now, in practice, we usually look at a collision immediately before and immediately after. We write out that law of conservation of momentum. The initial equals the final momentum. The initial momentum should be just before the collision takes place, and the final momentum should be just after, immediately after the collision takes place. How come? What's the reason for that? Yeah. Good. In other words, to make it as close to an isolated system as we can. If we look at just after a car collision, there's going to be friction acting on those cars as they're sliding across the highway, right? And if we look at 5 seconds after that collision, that friction is probably going to have taken a significant amount of energy and therefore mass away from the system. That's not good. That's not an isolated system. If we look at just after that collision, then although friction is acting, technically, it's had a very small effect, so it's a good approximation of an isolated system. Same thing before the collision takes place. Look at the collision just before it's taken place. If you look at it 3 minutes before, then all kinds of factors could have entered into play here, okay? We want to make it an isolated system, so we're going to look at the collisions just before and just after. One final thing. We talk about momentum staying the same in some kind of interaction. Momentum doesn't go up and it doesn't go down. But yet, we just finished talking about impulse, which is defined as the change in momentum. How can, in one breath, we talk about a change in momentum and then the next day be talking about momentum staying the same? A law that says momentum stays the same. Yeah? Good, excellent. If you're talking about impulse, you're talking about the change in momentum of an individual object within the system versus conservation of momentum. It's the total momentum in the system remains the same. You're running down a football field, you smash into a football player. Okay, maybe he loses momentum, you gain momentum. Okay, there's been 2 impulses there, right? The impulse or the momentum that's gained by you and the momentum that's lost by that football player. But the total amount of momentum stays the same. Okay, the total momentum of everything added together hasn't changed. Make sense? All right. We're going to use this to solve our problems anytime we have a collision or an explosion. And we're going to write down MV for every object both before and after the collision. So if we have 2 objects before, it would be MV plus MV. M1, V1 plus M2 V2. M1 V1 initial plus M2 V2 initial equals, we have two objects after the collision, they haven't stuck together, it would be M1 V1 F plus M2 V2 F. But if they do stick together because Velcro or just sticky or two cars hit each other and entangle, it's only going to be one object now. We'll just call it MVF. Good? One of the mistakes that I've noticed over the years, I don't know why people do this. I do know why people do it, but not sure how it happens exactly. People will say MV squared plus MV squared equals MV squared plus MV squared. Where do you think that comes from? Sorry? No? I don't think so. No, I don't think that's where it comes from either. It could be, but yeah, I think it's people mixing up momentum with kinetic energy, right? Momentum and kinetic energy are real closely related, and sometimes people mix those two quantities up. MV squared is nothing, right? 1/2 MV squared is, but I think what's happening there is people are kind of combining momentum and kinetic energy and making an equation that just isn't even an equation. So be careful with that. MV, MV, MV. All right, two questions you had for homework, page 478. Any issues with either or both of those two questions? Yep. Yep. Anybody for number 2, or is that good? Just number 1? Okay, let's go through that. Identify what's going on, because that's what we like to do first. And then let's write down our givens here. A 0.25 kilogram volleyball is flying west. As soon as I see that word west, I should circle it because it means negative, right? Draw attention to it. At 2 meters per second, when it strikes a stationary 0.58 kilogram basketball dead center, the volleyball rebounds to the east at 0.79. What's the velocity of the basketball immediately after impact? This is a collision, right? I think it's pretty clear that this is a collision. What do we do whenever we have a collision? That is, if we're looking at the system, what do we do every time we have a collision? Yeah, conservation of momentum. If we wanted to look at one of the objects, the volleyball or the basketball, and not the other one, then we technically could use impulse. Let's first make number 1 the volleyball, and let's make object number 2 the basketball. This makes this M1, this M2. This is going to be what? V1, clearly it's a velocity, right? Is it V1 or is it V2? The volleyball is object number 1, and the volleyball is flying west at 2 meters per second. V1 or V2? V1. V1I or V1F? V1I, it's the initial velocity. Whenever I do this, I feel like I'm at the eye doctor's. You know what I'm talking about? Is it 1 or is it 2? 1 or 2? They go back and forth. A couple years ago, I was at the eye doctor, and she says, 1 or 2? Can you see 1 better or 2 better? And I'm like, can't see anything. All I see is bright light. She says, oh, I forgot to put the slide in. I thought I was going blind. But then she puts the slide in. Sometimes it's still hard to tell which one's better, but at least I could see something. Object number 1, initial. Okay, strikes a stationary 0.58 kilogram basketball. This means that V2 is 0, right? V2 what? V2I or V2F? V2I, the initial velocity of the basketball. The volleyball rebounds east at 0.79. V1 or V2? The volleyball rebounds east. That's going to be V1, right? The volleyball is object number 1, and it is going to be V1F. Finally, we're looking for the velocity of the basketball after impact. That's going to be V2F. So there's a lot of stuff there. It's always important to write down givens, particularly in these conservation of momentum problems. There's 4 velocities. V1, V2, initial, final. That gets confusing if you don't identify explicitly what those variables are. Okay, whether you write it down like I have, or whether you write it down the old-fashioned way, okay, like most of you did in your notes there. Doesn't matter. Just write them down somehow. Okay, we say Pi equals Pf. How many objects do we have before this collision takes place? 2. There's a basketball and there's a volleyball. M1 V1I plus M2 V2I. And how many objects do we have after the collision's taken place? Okay, I thought you were saying 1 there for a second. There's 2 objects. They bounce apart. Okay, so there's 2 objects. We're going to say M1 V1F plus M2 V2F. Hey, can I cancel the masses out here, by the way? Okay, so I can get rid of that term. Yeah, I can get rid of that term for sure, because not because of the value of m, but rather V2I is 0, and whatever M2 is times 0 is 0. Can I get rid of those m's? No. Can I ever get rid of those m's? Yes, but not in this question. Give me a situation where I could get rid of those m's. Where I could cancel those m's out. Again, was your hand up? No? Kevin? Yes. If you've got something like billiard balls hitting each other, right? Then they're all the same mass. And if it's the same mass and it appears in each term, then we can cancel that out. Does that make sense? If in doubt, just leave it, right? Because you'll get the same answer even if you don't cancel them out. Okay, M1 is 0.25. V1I is negative 2.0. I didn't forget the negative because I circled west in red as soon as I saw that. V1F is east, positive 0.79, plus M2, which is 0.58, times V2F. Let's pull out the calculator here and make sure we can solve this now. Say 0.25 times negative 2 gives me negative 0.5. Let's subtract from that and make sure you use some brackets here. 0.25 times 0.79. Hey, why did I subtract that? Right, I'm bringing it over, and on the right-hand side, it's a positive. You got to bring it over to the left-hand side as a negative, right? So that gives me negative 0.6975. Let's divide that by 0.58 now. And when we do that, we get negative 1.2. So V2F equals negative 1.2 meters per second. And you can see here that I made west negative and east positive. So that negative means 1.2 to the west. Right? Good? Tristan, is that okay? In both of these questions, if you've done them, and all of you have, all of you who were here yesterday have, I think you would have recognized that object number 2 is at rest before the collision takes place. We're going to do a question right now where object number 2 isn't at rest, where they're both moving. That doesn't make it harder. It just makes it a tiny bit more work, because instead of crossing off this term right here, we have to include it. Let's do that problem now. 9.8 on 479. This one says 110 kilogram Stampeders football fullback is moving east at 1.8 meters per second on a snowy playing field and is struck by a 140 kilogram defensive lineman moving west at 1.5. Okay, I don't care what's going on right now. I noticed the word west. I'm circling it because I think I might make a mistake with the negative if I don't circle. Fullback bounces west at 0.25. It's the velocity of the defensive lineman just after impact. Notice it says just after impact. Why does it say just after impact? Adam? He would slow down more later because of friction and falling and whatever, right? And if he slowed down because of friction or falling against the ground, whatever, that would make it not an isolated system, right? Okay. We're looking at just before and just after. Okay, it's a collision. Conservation of momentum applies. Let's write down some givens. Object number 1 is going to be the Stampeders player. Object number 2 will be the Eskimos player. That makes this one M1, this one M2. V1 or V2? 1.8 meters per second, V1, V2. V1. V1 initial, V1 final. Good. V1 initial. It's the initial velocity of the Stampeders player. The Eskimos player is moving to the west at 1.5. That's going to be V1 or V2? V2, the Eskimos player. To the west at 1.5. Is that initial or final? It's going to be initial, V2I. The fullback, who is the Stampeders player, that's going to be V1 because it's the Stampeders player, V1F. Okay, representing his velocity or her velocity. I guess it would be his. Don't see too many hers for the Stampeders. At 0.25 meters per second, what's the velocity of the Eskimos lineman just after impact? We're looking for V2F. Again, lots of givens, lots of things to keep straight with signs, positives and negatives. You keep all those things straight and you're probably good to go on this question. We get two objects before the collision and two objects afterwards. I'm going to make a mistake or two here, and I want you to correct me when I make it. Everybody see where the mistake or mistakes are? Jake? Okay, good. The 1.50 should be negative. How come? It's to the west. I shouldn't forget that because I have my attention drawn to it with the red circle, right? Is there anything else, or is that it? Tristan? Yeah, the 0.25 is also to the west. It's also negative. And again, I shouldn't miss that because it's circled in red. You can see, though, that if I do miss that, then you're going to get the wrong answer. And if it's a multiple choice question, you can be pretty sure that that's going to be one of the options, right? Okay, let's calculate this one as well. Say 110 times 1.8. Let's subtract from that 140. Use some brackets here. 140 times 1.5. Okay, that's the left-hand side. Let's add to that brackets 110 times 0.25. Why did I add that? What did I add? There's no negative in front of the 110. Why shouldn't I have subtracted that from the left side? Yep. Right. This ends up being negative whatever, right? Doesn't matter whether I put the negative here or here. It's a negative term on the right-hand side. So take it over to the left-hand side by adding or by subtracting a negative. Okay, that gives me 15.5. Let's divide that by 140. Oops, divide it by 14. Let's divide it by 140 now. And we get 0.11. Should be 3 digits, right? So it's 0.111. It's a positive value, so that it means the Eskimos player after the collision is moving to the east. Yeah. Good? Because I got a positive answer. And if I get a positive answer, that means east. If I get a negative answer, it means west. If I go with the typical sign convention of east, positive, west, negative. Okay, if I get a negative value here, it would have meant west, because to go back to the original question, I made west all negative. So what's the difference between this question and the questions that you guys had for homework and did very well on? Not much. Simply object number 2 isn't at rest now. Object number 2 has momentum. Therefore, instead of getting rid of a term, I have to have all 4 terms in here. one of the things that people say sometimes after a test is, I did all my homework and the questions on the test were just hard. Here's the thing. Okay, first of all, some of the questions we do in class are hard too. Okay, remember those ones, because it's not the easy ones that typically go on tests, right? So remember the hard ones. Don't remember the easy ones. Remember the hard ones. They're the ones that go on tests. Okay, secondly, you could absolutely get something like this on a test, but it wouldn't likely be a 4-line thing like this. It might be a half a page or even a full page. They might tell you about the football game and the weather at the football game. And they might tell you how many people were in the stands at this particular Labor Day Classic in 1997. Whatever. They might give you a whole ton of information, but buried somewhere in that information is this. Okay, our challenge is to find this buried in that information. Okay, strip away the fact that there was 38,000 people at the game. Who cares? Strip away the fact that it was minus 16 degrees Celsius on that day and that it was snowing. It doesn't matter. Okay, what matters is what you see right here. Okay? If you can do this question, you should be good with any conservation of momentum question that you get on your test. Okay, let's take a look at these two questions on 479, please. Any issues with questions 1 and 2 here? I know there's a couple of you still working. If there's no trouble, though, we'll move on here. If you're having some trouble, then please raise your hand and I can help you out with it. When you're finished these two questions, if you've had no trouble with either one of them, then I'd like to assign the first part of worksheet number 3 for homework. Okay, right now, you can do up to question number 5 on worksheet number 3. The entire thing will be homework, but I'm going to allow you to work on questions 1 to 5 right now for the next, we'll say the next 8 minutes or so, 8 or 9 minutes. Okay, give you a head start on that homework for tonight. So keep working on 479 if you're not finished, but if you are finished those two questions, then get a good head start on worksheet number 3, questions 1 to 5 over the next 9 minutes or so. If you've had a chance to work on your worksheet for a little while, we're going to assign the rest of it for homework. What I'd like you to do right now is multiple choice. It's actually numerical response. Question number 10. I believe it's on page 13 of your notes, of your worksheet handout there. Please do that one. Please submit the answer here. Submit the answer for this one as numerical response 1. Okay, you're going to see when you go to the page, the submission page, multiple choice 1, 2, then numerical response 1, 2. You're going to submit it as numerical response number 1. Okay. 25 responses. Every single person picked C, which, sorry. 7.07, I mean. C and 7 start with the same sound, right? C and 7. The answer is 7.07. We're not going to bother going through this question because clearly all of you understand it if we all got the correct answer here. 7.07 is the correct answer. Big thing here is they lock together, so the total mass after the collision is going to be 3,300 kilograms, okay? One object, 2 objects before, 1 object after, 3,300 kilograms. Let's take a look at this one, please, at number 13, and submit that, please, as multiple choice number 1. Okay, multiple choice number 1. All right, let's take a look at this one now. 90% of you said D, 5% of you said C, and 5% of you said weren't sure, option E. So let's take a look here. We've got an empty freight car of mass M coasting along a track at 2 meters per second, coupling to, so combining with a stationary freight car of mass 2M. That's a collision. It's conservation of momentum. We'll call this one object number 1. We'll call this one object number 2. We'll call this one V1 initial. We'll call this one V2 initial, the stationary freight car. V2I is equal to 0. We want to find the final velocity or the final speed of them. That's going to be VF. They're combined, so we're not going to break it down into V1F or V2F, just VF. We'll say PI is equal to PF. We'll say M1 V1 initial plus M2 V2 initial equals MVF, one object after the collision takes place. This one disappears because V2I is equal to 0, right? It's stationary. So V2I is equal to 0. Now M1, we don't know what the number is. but we do know that it's m. They're calling it m for whatever reason. V1I is 2.00 meters per second. The combined mass after they stick together is what? 3m. Okay, if we have m and 2m combining, then it's going to be a total mass of 3m. We multiply that by the final velocity, and it looks like we have two unknowns here, m and vf. What do we do? M appears in both terms, right? So what can we do with it? We can cancel it out. If it's the same thing appearing in both terms, we can cancel it. VF becomes equal to 2 over 3, which is 0.667 meters per second. So it's a good thing that 90% of you said D, because that's what the answer is D. It's a good question. You guys did a good job on that too. In the end here, guys, this question is one of those ones that we expect to see on tests, right? Because it's not just quite, here's the mass, here's the velocity, whatever. There's a little bit of a something to it that you got to think about, right? That's the whole idea of not knowing what the mass is. Okay, but you can see that we're still okay with that. Okay? So here's your homework for tomorrow, guys. Check on the FUD questions, what I assigned before, 467, number 1 to 13. We'll make that worksheet due for Thursday. The worksheet due for Thursday for you, okay? You know what, we'll make it the whole thing, but we're going to try to do one more problem tomorrow that will allow you to do questions 6 and 7. So we'll say right now the whole thing will be due on Thursday. We have to do one more question first, though. Okay? Have a good night, guys.